In this video, we will see that if we have a continuous function that happens to be invertible, then its inverse is also continuous. So how can we prove this? Well, before we start with the proof, I want to recall some definitions. We know that f is strictly increasing if I know that x1 less than x2 implies that f of x1 is less than f of x2. We said that f is strictly decreasing if x1 less than x2 implies that f of x1 is greater than f of x2. And we say that f is strictly monotonic on an interval I if it is either strictly increasing or strictly decreasing. Okay? So with these definitions, we're going to have this, that if I know that a function is continuous and invertible, then it is monotonic. And actually not just monotonic, it's strictly monotonic. So, as I said, if f is continuous on an interval I and has an inverse, then f is strictly monotonic in the interval I. And how do we prove this? Well, we're going to suppose, for the sake of a contradiction, that f is not strictly monotonic. Then there exist 3 points, x1, x2, and x3, such that x1 is less than x2, less than x3, but f of x2 is not between f of x1 and f of x3, right? If it were strictly increasing, then it would be f of x1 less than f of x2, less than f of x3, and if it were strictly decreasing, it would be f of x3 less than f of x2, less than f of x1. So we know that because we're assuming that our function is not strictly monotonic, f of x2 is not between f of x1 and f of x3. Good. Now, without loss of generality, we're going to assume that we have that f of x1 is less than f of x3, that is less than f of x2. Now, my function is continuous, so I can apply the intermediate value theorem. And by the intermediate value theorem, then I can find a point x0 between x1 and x2 such that f of x0 is equal to f of x3. And something that is very important to point out is that x0 cannot be equal to x3 because you see x0 is in between x1 and x2, and x3 we said that was strictly bigger than x2. Then we have 2 points that are different that have the same image. Well, that means that f cannot be injective, so f cannot have an inverse, because to be invertible, we need to be both injective and surjective. And this is a contradiction, so then we know that f must be strictly monotonic. Now that we have this, we're going to prove the main theorem of this video. It is that a function f has a domain on interval I. If I know that f has an inverse and f is continuous in its domain, then the inverse is also continuous on its domain. So how are we going to do this? Now, because I know that f is continuous on that interval I, the intermediate value theorem implies that the set f of x such that x is in I forms an interval j. Remember, we said it earlier that the intermediate value theorem tells us that continuous functions map intervals to intervals. So if we start with an interval, the image of that interval should be another interval. So the image of the interval I is going to be some interval j. Good. Now we're going to assume that A is an interior point of j. So we take a point A inside j. Now, from the previous theorem, we know that f is strictly monotonic because we said that if a function is continuous and invertible, then it's strictly monotonic. But now, if my function is strictly monotonic and A is an interior point of my interval j, then that tells me that the pre-image of A has to be an interior point of I. Because you see, if we're an endpoint of the interval I, that would actually get sent to an endpoint of that interval because my function is strictly increasing or strictly decreasing. Okay, now you see, we're going to pick an epsilon positive. Then for that epsilon, we can find an epsilon 1, still positive, but less than epsilon, such that the interval that goes from the preimage of a minus epsilon 1 and preimage of a plus epsilon 1 is contained in my interval I. So what we do is we take this point, which is f inverse of a, and we get an interval, a teeny tiny interval centered at f inverse of a, and we take epsilon 1 small enough to make sure that this interval that we create is still contained in that interval I that I have. Good. Now I have this, and because f is strictly monotonic on the interval I1, then its image forms an interval, which we're going to call J1. And you see, we're going to pick a delta small enough such that the interval centered at a of radius delta, so the interval a minus delta to a plus delta, is contained in the interval J1. Why do I do this? Because you see, if I pick a point y whose distance to a is less than delta, that means that I am in the interval, that y is in the interval a minus delta, a plus delta. That means also that y has to be in the set J1. But you see, if y is in the set J1, well, we know also that then y is equal to f of x for some x in the interval I1. Right? So then that means, well, that the preimage of y is in the interval I1. But the interval I1 was this one that had all the points within distance epsilon 1 of f inverse of a. So that tells me then that f inverse of y minus f inverse of a in absolute value is less than epsilon 1. But epsilon 1 is less than epsilon. And that's exactly what I wanted to prove. This tells me that the limit as y approaches a of f inverse of y is f inverse of a, which actually shows that my function is continuous at a. We did this proof for interior points of the interval, but we can do a similar proof when we consider the endpoints of the interval. I'll leave that one up to you.